So we're now beginning the lectures on quantum mechanics. So now that we're dealing with quantum mechanics, I want to start with the most basic or the deepest difference between quantum mechanics and classical mechanics. And that really deals with something called states of a system. What are the states of a classical or quantum system? It's just everything that you can measure about that system. If I take a real simple system, something like, say, a coin right here. A coin, when I flip a coin right here. Now, I don't care about what the denomination of the coin is. I don't care about the metal or where the coin is. All I care about is the heads or the tails. So the states of this system, a coin, so for a coin, there's just a two-state system. It could either be a head or a tail. Okay, there are other two-state systems that may be one that's even more popular, and that is the bit, the computer bit. So if we just look at something called, we'll call it the C bit. C could either stand for computer bit or classical bit. And we know that you could either be a 0 or a 1. It's a two-state system. Well, these are just classical bits. So first we're going to look at the classical systems, then we'll see how they differ from the quantum systems. Well, what can you do with one classical bit? Well, there's only two things you can do. You can either leave it alone, or you can flip it to the other one. Usually when we flip it to the other one, we put it through a gate, something called a NOT gate right here. And it looks like this right here. That is, if I put in A here, if A is a 0, then out comes a 1. If I put in a 1, out comes a 0. So this is the output right here. And so if I just come over here and say A, if A is a 0, the out is a 1. If A is a 1, out is a 0. So you could, I think when I was teaching 4B, we were making these gates right here. You can make them with transistors and with voltages. Okay, this is about all you can do with with just one C bit. I mean, you could say do nothing, but I don't need a gate for that. Well, what if we have two C bits? Right? Then we can do a little bit more with it. We can do, if we have 2 bits, so now we have 2 C bits. We could do something, say, OR. We could OR them together. OR. The symbol for that looks something like this. So now you've got 2 C bits, say A and B, and this is the output. Or mathematically, you'd write it as A, or is a lot like a plus, so we write it like this, A or B. Now the table for it, A, B, and you have an output over here. There are 4 possibilities for the input. They can both be 0. They could be 0, 1, 1, 0, or 1, 1. Those are the only 4 possibilities. Now, since OR works exactly like a plus, 0 or 0 is just going to give me a 0. 0 or 1 is a 1. 1 or 0 is a 1. But 1 or 1. Now, there are 2 types of OR gates. One is called an inclusive gate, inclusive OR. That means if any of these are 1 or if they're both 1, you get a 1. That's the one we're looking at, inclusive OR. There's also something called an exclusive OR that says it has to exclusively be one or the other. But I'm not looking at that one. This is an inclusive OR. Okay, so there is the OR. Now you'll notice if I swap the order of this, A or B, it's the same thing as B or A. You notice if I swap these two columns, the other one still stays the same. And it's just like when you say you're going to do this or that, it's the same thing as saying you're going to do that or this. There's no difference. This is all called Boolean logic or classical logic right here. Now, besides or, there's also the and. The and. Okay, and we write that as a multiply. And the symbol looks like, the gate for it would look like this. A, B, and out right there. Works like a multiplication. That is, if we put in our truth table, they call this a truth table right here. A, B, and out. Four possibilities, 0, 0, 0, 1, 1, 0, 1, 1. Then this is like a multiply. Multiply, this is the and, just to remind you. It's like a multiply. This would give me a 0. 0 times 1 is like a 0, 0. 1 times 1 is a 1. So when you say you're going to do this and that, means you have to do both to be true. Okay, so this is just all classical logic or Boolean logic. Now this is just a two-state system. I should say from this gate and this gate and this gate, you can build an entire computer with this. These are the basic building blocks for the microprocessor, for any digital electronics you can make. All bigger components are made from these three. Well, let's look at a bigger system than a two-state system. How about a dice? One dice is not a dice, it's a die right here. If we look at a die, okay, whoops, sorry. You got a 1, you got a 2, you got a 3, and so on. That's a six-state system. You got a 1, 2, 3, 4, 5, and 6. There's only there's 6 possibilities, so it's a six-state system. And in that case, we could make up a proposition for this die. We could say proposition 1. Proposition 1 is, say, the die is even. Die is even. Okay, well, if we want to say it's even, then that corresponds to just all the even numbers. So that would be just those right there. We could also put a separate proposition, say proposition 2. How about the die is less than or equal to 4? Die is less than or equal to 4. Well, that gives me all of these right here. Well, now that I have these two propositions, I can now, we don't usually use and or for this. We usually use intersection and union, which is the same thing. So if we just said, maybe I should say, instead of proposition 1, I'll call it proposition A and B. A and B. So now we can say, what is A union B? Well, that's everything that's in both the blue and the red. So it looks like it's all of them but 5. So that one is 1, 2, 3, 4, and 6. And we can also see that that is the same as B union A. B union A. We can also, so this is very similar to the OR right here. And we can say A intersect B. That's what's in both. Well, the only thing that are in both, it looks like it's just the 2 and the 4. So that would be 2 and 4. And that also is equal to, if I reverse the order of it, B intersect A. Okay, it's the same thing. This is set theory. Set theory is exactly like we did down here, but this is just for a two-state system. This is for as many as you want right here. We use intersection and union instead. Okay, well, what about for classical mechanics? What do we use in classical mechanics? Well, let's look at a simple system. Let's say you have an object in one dimension, just along the x-axis. So an object can only move along the x direction. What are the states of the system? Well, the states of the system for a particle is just going to be what is the position, x, and what is its momentum. In this case, it's only in the x direction because this is in one dimension. So it's all the possible x and momentum in the x. Matter of fact, let's put on the y-axis here, let's put the possible momentums, px. Well, it looks like since this particle can be anywhere on the x-axis, plus or minus, and since the momentum can be positive or minus, depending on which way it's going, it looks like every point on this xy, xpx plane is a possible state of the system. So that is, the particle could be at, say, x equal 5, and the momentum, px, could be, say, 12. So it could have that would mean it was right there and has a momentum this way of 12 units. Okay, so every single point on here is a possible state of the system. So it's an infinite number of states. Well, the only thing is this point isn't going to just sit there, it's going to move right here. And especially we know it's moving because it has momentum. So this point is going to be somewhere else later. What determines how this point moves around on this space? It might be going off, like this right here. What determines that? That's just Newton's laws. So Newton's laws give you what? The evolution of that point, the time evolution. Give the time evolution of the state. Now, as this thing moves, there's a few things that this thing can't do. As it moves around, it could go all around. What it can never do is come back and cross itself. Right there. That can never happen. As it moves around here, it can never cross itself. If it did, that would mean when it was right here, it wouldn't know which way to go. You notice with Newton's laws, they give you a unique solution to what happens in the future. Exactly. Not only in the future, but in the past. So you couldn't even have some line come in and then catch back up to it, because if you were right there and went into the past, you'd say, I don't know which one it is. There's two possibilities. So as this thing moves around, it can't cross and it can't combine. There's got to be a unique point in the future and a unique point in the past. It's just the way Newton's laws are, and so it kind of goes around. Now, we could do it, let's just look at it for a nice simple system. How about a mass on a spring? Let's say we have a mass just sitting here going back and forth on a spring. And I said, what is that going to look like? I'll draw it down here. What is that point going to look like? X and px. Well, what's the equation for a mass on a spring? What determines it is Newton's laws, but Newton's laws and energy equation are the same thing. It might be easier for me just to write out the energy. The energy is 1/2 mv squared plus 1/2 kx squared equals E. Now, if there's no friction or any energy loss, then this is a constant. It doesn't have to be, but now what I'd like to do is I'd like to turn my this into momentum right here. Well, we know that the kinetic, at least classically, this is all classical, not relativistic, non-relativistic. We know E is what? P squared, px squared over 2m. That's the same as the kinetic, because if you plug in mv and divide, you get 1/2 mv squared, plus 1/2 kx squared. And then I'm going to divide everything by E. So this is just 1 equals px squared all over 2me plus x squared all over 2. I'm going to take this k and bring it down below so it's 1 over k. And we have the E also, because we divided out the E. Now, if you look at this, what do we have? This looks like 1 equals px squared. Well, my px was really my y on this case. It's y squared all over some constant c1 plus x squared all over some other constant, c2. Well, this looks like the equation of an ellipse. So this thing would just be an ellipse right here. So it's just going to go around like that. When you're over here, this is when the x is a max and your velocity is 0 because your momentum is 0. That's when you're way out on the end. When you come back to your equilibrium position, that's where x equals 0. You've got a very large speed both ways. One, when you're coming back, or this would be when you're coming back, and that's the way when you're going forward. And likewise, when you're way over here compressed, that would be over here at this point. So this thing is just going around like this. It's not violating this rule we have up here. It's just overriding itself. So this would be the mass on a spring. Now, if it was losing energy, it would just spiral inward, and eventually stop right there because the momentum would be 0 and it'd stop right at the equilibrium spot. Okay, so you'll notice if we had to put in 3 dimensions, then I couldn't draw that because I'd have to have an x-axis, a y, a z-axis, a px, a py, and a pz. That would be a 6-dimensional space, a point moving around. I can't draw a 6-dimensional space. Now, when you compare this with quantum mechanics, remember we had something called the Heisenberg uncertainty principle. One of them was the uncertainty in the x times the uncertainty in the momentum was greater or equal to h. So I can't get a point. That's impossible with quantum mechanics because I'd have to know that point. I know both the x and the p. So quantum mechanically speaking, no, this would be like a region right here. I'd have a little region where I have some delta p and you'd have some delta x. All I could say is it's somewhere within this region. And the more I tried to squeeze this, the more this would stretch out. And the more I tried to squish this, the more it would stretch out like that. So we can see that quantum mechanics is going to be a lot different than this. We can also do the same sort of propositions that we did with the die. We could have said proposition A is let's just say the particle is between this x value and this x value. So we could say that's the one proposition. It's between x equals 2 and x equals 3. And then we could have made another proposition, whereas the momentum was between here and here. The momentum was between, say, 1 kilogram meters per second and 2 kilogram meters per second. And so that would be this region. And now we can say, what's the intersection? That is, what is the intersection between x has to be between these 2 points and p has to be between these 2 points? Well, that would just be this little rectangle right there. And we could have talked about the union. That is, x is between here and here, or momentum is between here and here, and that would be all of this region. So even classical mechanics uses this regular set notation, this classical logic, Boolean logic. So this is classical mechanics. Okay, so now we want to go to quantum mechanics and say, what are the states of a system? Quantum mechanics. Okay, so the states of a system, I want to get this down right here. It says the states of a system are all the normalized vectors in a complex vector space. Okay, so it's a lot different than this. This is all set theory. This is all vectors. It's a completely different math to it. They give a name for this vector space. They actually call it the Hilbert space. Hilbert space. Okay, so now, first of all, we already know what we mean by normalized vector. Normalized, these would be complex vectors because they're in a complex vector space. Normalized vector means the length of the vector, the magnitude of the vector is 1. So we know that. And then we want all the normalized vectors in that vector space. Now, just to give you a little, suppose we have we wanted to figure out what all the states are of a system, normalized vectors instead of a complex vector space, let's just say a 3-dimensional real space like you had in 4A. So what would that be? Well, if you could draw 3 dimensions, we would call it I, J, K, I guess, or X, Y, Z. Now, if you draw a sphere, a unit sphere of radius 1, so this thing has a sphere of radius 1. So this, I better write that down, radius 1. Now, if we were to look at every single vector that starts at the origin and goes to the surface of the sphere. Start at the origin, go to the surface. Start at the origin. There'd be an infinite number of them all in different directions, all coming outward right here. Those would have been all of the states, possible states. Well, those would be all the normalized vectors in this real 3D space. Okay, so whenever we talk about all the normalized vectors, you could probably think of it something like this. Or what if it was just a 2-dimensional space? Well, then you'd only have IJ. I, and j, there would be no k. And so instead of a sphere here, you'd have a ring. You'd have just a ring, a unit ring right there. And so every vector that starts at the origin and goes to the ring, these would be all, this is a radius of 1, these would be all the normalized vectors in that real two-dimensional space. And these would be all the states of the system, quantum system for, well, I shouldn't say quantum because we're normally in complex, but these would be all the normalized vectors in this real two-dimensional space. This would be all the normalized vectors in that real three-dimensional space, just to give you an idea of what it looks like. Okay, so now we need something on, say, notation. How are we going to notate our vectors? Remember before in 4a, we notated it like this. We said f was something like, I want to use the exact same. How about 5 in the I plus 4 in the, let's say 3. Say 3 in the I plus 4 in the j plus k. Say we've got this vector. First of all, this vector is not a normalized vector. Why? Because normalized vector means the magnitude is 1. What is the magnitude of this vector? Well, it's the square root of this squared plus this squared plus that squared, the numbers. So it's 9 and 16 and 1. 9, 16, and 1 is 26. So the length of this vector is the square root of 26. So if I wanted to turn it into a unit vector, I just divide every term by 26, square root of 26. 26 square 1 over the square root of 26. So now it's a unit vector. It's one of these vectors up here since we were in 3 dimensions. One of these green ones is that vector. Now we're not going to use this notation for our vectors. For this, for the force, we're not going to put a little arrow over it. We're going to write it like, I won't even use f. How about if we use, well, we'll use f. F. We're going to write it like that, where this is a straight line and that's, looks like a greater than symbol, but we're going to write it like this. They give a name for this symbol. It's called a ket. Okay, and over here on this side, we can't do it like this because we're going to have sometimes more than 3 dimensions. You know, you can even have infinite dimensions. We said we were going to write it as a column of numbers. So this is this, and for this case, it would just be 3 all over the square root of 26, 4 over the square root of 26, 1 all over the square root of 26. And we know, since this has to be normalized, the square root of this squared plus this squared plus this squared has to be 1. Actually, since it has to be 1, you don't even have to take the square root of it. It's just this squared plus this squared plus this squared better be 1. Okay, so there is our vector notation right here. So we're going to use this notation. Remember, it's a straight line and then greater than. Okay, so now let's look at just some, I think we went through these vector rules before. We said if A is a vector in the space, is a vector in our space, then if we multiply it by a constant, say alpha A is also in that space, is also in our space. Which is good because, remember, before we normalized this, that was in that space, and then we multiplied it by 1 over the square root of 26. That's still in the space, so that allows me to always normalize it right here. Remember, we always want to work with normalized vectors. Okay, and so there's one rule. So this would be a vector rule, I guess. Vector rule. And this is one, and then the second one is if A, I think we did this one also already, if A is a vector in our space, is a vector in our space, and another vector B is also in the space, is also in the space, well then A plus B is in the space, in the space. Well, remember, all these are states of a system. So A can happen and B can happen. And then this is saying if A can happen and B can happen, then A and B can both happen simultaneous. That's a lot different than over here. You can't say two things happen simultaneously over here in classical mechanics. You can't say the ball is here and there at the same time. But here, if A can happen and B can happen, then both A and B can happen at the same time. And we even had that with our double slit. When we had our double slit here, and we were throwing our electrons through. Well, the electron getting through this could be state A. The electron coming through that could be state B. And what did we say? Didn't we say the electron can go through both holes simultaneously? So A or B is also a solution right here. Now, remember, if A was normalized and B is normalized, then A plus B probably isn't normalized, but I can normalize it by multiplying it by a factor. So that means instead of writing A plus B, we could have said, I don't know what else to call it, say psi is equal to alpha A plus alpha 1A plus alpha 2B. That's also got to be true. That way I can normalize it. Remember, to normalize it means that this vector has to have a length of 1. We already know A has a length of 1 and B has a length of 1, but when you put it together, you got to put the right constants in here. Now for us, alpha can be a complex number because this is all a complex vector space. Okay. Okay, so now let's look at another, I don't know if we could call this a vector rule, or I think we can call it a vector rule. For every vector, for every vector A, for every vector, there is another vector associated with it. We call it a dual vector. There is a dual vector. And we're going to make it look like this. Right there. You notice how that one is backwards from this one right here. Okay, so this is the dual. The dual, for every vector, we have a dual vector. We give this a name too. We call this a bra. So this one's called the bra. This one over here was called the cat. Okay, so now, what does that do? How do you go from this vector to the dual of vector right here? Well, if A was, let's just call it, it's some list of numbers, A1, A2, I don't know how many you got, depending on the dimension of it. Then the dual of it, what you do is you turn it into a row, and every element you replace with the complex conjugate. That's it. So this is A1 star, A2 star, A3 star, and so on. So that's all it does. Okay. So let me just give you an example right here. Let's just let A equal to, how about 2i, 3, 1 minus I. Then what would this over here be, this A? Well, you flip it and you make the complex conjugate. So if you just flip it, it's 2i, 3, 1 minus I, but then we do the complex conjugate, so it'd be minus 2i. The complex conjugate of 3 is still 3, and this would be 1 plus I. So that's what so you just turn it into a row, take the complex conjugate of each one right here. Okay. What happens if it's written like this right here? What's the bra of psi? That is, what is this right here for this? Well, you turn all of these into bras, and you turn these into complex conjugates. So it'd be alpha 1 star bra A plus alpha 2 star bra B. So that's how you turn any vector into its dual vector. So that would turn this into its dual vector. Now, let me just suppose I had, let's just say A was, how about just an easy one, like real, I'll just put some real numbers in. 1, 2, 3, and B is 2, 3, 4. Now I ask, what is A, B? These two pair up a lot. Why? What is this called? This is called the bra. This is called the ket. Put together, what does that make? It makes a bracket. So that's where the name bra and ket come from. So what would this be for these two numbers here? Well, for A, you turn it into a row and make it the complex conjugate, but the complex conjugate is the same because it's real. 1, 2, 3. This we don't change. It's 2, 3, 4. If we multiply these together, we already know how to do all that. This is 2 plus 6 plus 12, which equals 20. Now, you'll notice this looks a lot like our dot product from 4a. Remember, for our dot product, what did you do? You multiplied their x components together, you multiplied their y, and you multiplied their z, and you added them up. Well, that's exactly what we're doing here. So this is exactly like the dot product. So this is just like the dot product. What does the dot product give you? It gives you how much the two vectors overlap. If two vectors are like this, they overlap quite a bit. If they're like this, right on top of each other, they overlap completely. If they're perpendicular, there is no overlap, and that's 0. So if you got the 0 out of here, it would mean that these two vectors are perpendicular to each other. Okay, so that'll mean a lot in quantum mechanics. It's just the overlap. What if we have something like, what if we flip these two? What's the difference between A, B, and is that the same as BA? Right here. B, A. Does the order, normally for A, it didn't matter. A dot B was equal to B dot A. But this case, it does matter because these are complex numbers. And so when you flip them, you're actually doing the complex conjugate, because when you turn this into that, so we're turning a column into a row, which means we're taking the complex conjugate. And here we're taking a column and turning it into a row. So what this does is, if you swap the order of it, it's the complex conjugate of it. Now, what if these two are the same thing? What if it's AA? Anytime they're the same, AA. Well, if we flip the order of them, you couldn't tell, but that A is the same as that one, and that one's the same as that one. I flipped them, but you can't tell. That should still be true. Well, these two are the same, and anytime you equal your own conjugate, that means this has to be a real number. So this is always real. Always real. Should never be, this one down here, this could be complex, A and a B, but anytime you're dotting it with yourself, BB or even psi, whatever it is, this is always real. Not only that, remember, all of our states are normalized vectors. So the magnitude of A and that has a magnitude, they both have a magnitude of 1. And remember, when you do the dot product, it's the magnitude of A, magnitude of B times the cosine of the angle between them. The angle between A and A is 0, so it's just 1 right here. And so this dot product, it's not only always real, but always 1, and 1, and 1 right here. It's always going to be 1. Remember, because this is a dot product between two normalized vectors with itself. Okay, so we've got that right there. So now we can come up with our second rule. Our second rule for quantum mechanics. Our first rule is right here. There's only going to be only a handful of rules in quantum mechanics. But this is rule 1 for quantum mechanics. The states of a system are all the normalized vectors in a complex vector space. And our rule number 2. Rule 2 is this quantity A, B, right there. This right here is this is the probability amplitude of measuring state A if in state B. So if you're in state B, this first one, and you ask, what is the probability amplitude of measuring state A? You just do this dot product. Now this isn't the probability, it's just something called the probability amplitude. This can be a complex number. You can never have probabilities that are complex. I'm not done with this, and, I better write out, and, how do I make it real? You multiply it by its complex conjugate. And this, A, B, squared. What does that mean? That means you're multiplying this by its complex conjugate, this whole thing, so it's real, and positive, is equal to the probability not the amplitude. This is just the straight probability of measuring state A if in state B. Okay, so this will help us get the probability amplitude, but then when we multiply this whole thing by its complex conjugate, that'll give me a probability. Remember, this number right here is not only is it always positive, but it better be a number, it can't be bigger than 1. Because if you're dotting two vectors, unit vectors, remember, it's usually the magnitude of one, magnitude of the other times the cosine of the angle between them. Well, the cosine is a number less than 1. So you're multiplying 1 times a number less than 1. So this cannot be bigger than 1. You can't have a probability more than 100%. So this value, this value right here, value should be real. Real and somewhere between 0 and 1. Between 0 and 1. You can only have, remember, 1 is 100% probable and 0 is a 0%. It's got to be between that right here. So that is our second rule of quantum mechanics. And you'll notice, didn't we say this, anytime they have the same number, you always get 1. So that means if you're in the state A, and I ask what is the probability of measuring it in state A, well, it's 100% right here. Because you're in state A. Right? If you're in state B and if this was B and B, it should be 1 also. Or even if it's a mixture of states, if I say, if you had psi and psi, I don't even have to square it. If they're the same, I don't even have to square it, because if this is always 1, then I don't even have to square it, because then it's still 1 right there. So these two rules, this rule and that rule, is pretty much all we need for a little bit of time, right? And then we'll bring out some more rules. But you can see how different it is from classical. Now we're just dealing with vectors and vectors rather than set theory. Oh, yeah, we'll bring up that next time. Okay.